Monica Beckwith, and today I'm going to talk about the ARM ecosystem. So I work for ARM, and it's got this rich ecosystem, and how that works with OpenJDK, because ARM has a separate backend for OpenJDK. Most of the OpenJDK, when you go and download the binaries that you have, they're mostly for x86 architecture. Red Hat actually was the original porter for the AR64 backend. And I'm going to talk more about that and kind of talk about the upcoming performance optimizations, because my background is performance engineering. I've worked with the JVM and the garbage collector. So like I said, I work at ARM. I'm the principal JVM performance architect. And I work in the infrastructure group at ARM. My background, like I said, is a JVM GC performance engineer, about 15 years. I started at AMD as a JVM engineer. And before joining ARM, so I joined ARM in March of this year. Before that, I was an independent consultant, again doing performance optimization on the Java applications or Scala applications running on top of the Java virtual machine. And prior to that, I used to work for Oracle Sun, and before that, like I said, AMD. My last title at Oracle was G1 GC Performance Lead. So I worked with the garbage collector a lot, especially the G1, which is the default collector since Java 9. So I want to start with a little bit about ARM and its ecosystem, which is really important because ARM designs chips and like microarchitecture. And then we have partners that actually do the manufacturing, and you know, they build the servers. And so ARM is a designer, and we need to work with the partners, the ecosystem, to be able to make sure we are performant. And my field is Java, JVM, so I'm going to just concentrate on that right now. So what is the ARM enterprise ecosystem? I want to talk briefly about the JDK release cadence, because it's really important when you're doing a roadmap, OpenJDK performance roadmap. You want to align it with your long-term supported releases and non-long-term supported releases. For example, if you try to download JDK 10 on Linux, on ARM, you wouldn't find it, maybe, right? So you may have to go to adopt OpenJDK or something to get that, or Linaro will be supporting that too. So these kind of things are really important to understand, especially for where you're getting the binaries and or when the binaries are long-term supported or not. And then the stakeholders, which means the ARM ecosystem. And then I'll dive into the OpenJDK 9 plus, so 9 until 11, anything that's, what I like to do personally, I like to think in terms of performance, and then I like to think of latency, throughput, and footprint. So I'm going to kind of divide these projects, either that have gone into 9 and 10, or going to go into 11, into, or in the future, you know, past 11, into latency or footprint or throughput sensitive projects. And then I'll talk about the tools that we use internally at ARM, and some of them are native agents that are written by ARM employees and Linaro assignees. I want to show that to you. It's really helpful for profiling purposes. So a little bit about my group. We support the entire infrastructure. So we have an awesome lab. This is in Austin, Texas. That's where I live and work. We have more than 75 systems, and these are from various ARM partners. We also have legacy systems like x86, 64 systems. For comparison, when we're doing performance runs, we want to make sure that we're performant. ARM architecture is performant. Oops. OK. It's back. And then, of course, the Ethernet and the racks and everything. So this is having a stable environment like that, and then having an infrastructure on top of this hardware stack helps us to get consistent results. So we thrived for system consistency. We try to reduce run-to-run variability, so we have repeatable runs. We want to make sure that we can configure BIOS settings or anything like that that's necessary to understand, for example, prefetching, hardware prefetching. So how is software prefetching affecting hardware prefetching? So we want to change those settings. So we want to make sure that we can configure that on the go, so it's automated. We want to be able to profile the workloads and do workload characterization. So we want to make sure the automation framework is helpful in that. So for right now, we can deploy a fresh system on demand, basically deploy from scratch. We have known versions of OSs and any packages with it. We can sweep workloads, just run a test, and do the entire gamut of workloads, which I'll show you quickly. We can talk about core counts and cache sizes and 1P versus 2P systems. We can gather results, store, experiment, and do some preliminary analysis, store that into database as well. And we can test on virtual machines and containers as well. So the way we do it is we use Metal as a service. And then on top of that, we have Juju Charms for deployment. What the mask does, it powers on the system and deploys the OS and everything. It's also capable of doing different Linux distributions. The Juju Charms will be helpful in configuring your systems, basically how much load, core count you want, cache size, load generation, and it'll execute the benchmark and then do the data collection. We use MongoDB Jupyter for data collection and graphing and analysis, Jenkins for regressions and build services, Jira for development and tracking, repositories for any code revisions that we have. And this is, at a high level, how the performance analysis looks for my team. We have partner requests, IP teams, internal teams, and the community. So in my case, it'll be the OpenJDK community. That's going to drive how we identify a new workload. Then we do performance analysis. We make sure it's peer-reviewed. And then if there's any regressions, we keep on tracking the regressions and trying to analyze the regressions. And then the final report, either we improve the workload, because the workload was not really able to capture what we wanted to, or dependencies, or it goes into improving the architecture. So we feed back to the CPU teams, internal CPU teams. So these are the workloads that we have. I'm going to quickly go past these. We do have various spec tests, and then we have additional workloads, micro benchmarks. We also have the Java micro benchmark harness. We have some synthetic tests internally. And then we have SpecJ Enterprise next, which is the next version of SpecJ Enterprise. And it comes in full profile and web profile. And then various data storages also we test. So going to the ARM ecosystem. So ARM enterprise ecosystem, we want to make sure that we are standardizing open source, kind of across everything that ARM is deployed on. We want to provide enterprise class software support, and that includes tools and libraries. For example, HPC, we've done lots of work on HPC workloads. We want to make sure that we're able to power the next generation data centers, cloud, and network infrastructure. That's why Java is so important at ARM. So like I said, we do the design, and we have various silicon partners. Recently, you may have heard about Cavium's SpecJBB 2015 numbers, which were amazing, and with respect to the max JOPS and the critical JOPS, which is like a industry standard benchmark. And Cavium ThunderX2 performed really well. We have Ampere, we have HiSilicon, Qualcomm, Fujitsu, as various, and many more silicon partners. And then we have OEMs and ODMs. We work with all of these, Lenovo, Asus. So basically, this is a very rich ecosystem. what we really depend on is also making sure the OS operating systems work. And then we have like I said, we do virtual machine and stuff like that too. So we want to make sure the virtual infrastructure also works on ARM architecture. So we work with Fedora, Debian, and SUSE. Red Hat, we work, they have Oracle Linux, and then they have CentOS as well. And then our virtual infrastructure managers. We have various consortia. For example, Linaro, like I mentioned, for OpenJDK, Linaro is really important. So we have ARM assignees at Linaro. And then we have various others as well. These are the key applications that we work with. What is important to today's talk is this particular thing here, OpenJDK in Java. So for ARM ecosystem, like I mentioned, Red Hat was the original supporter of the backend, the AR64 backend. And then ARM has assignees at Linaro who helped with that port. Cavium works with Belsoft. They contract with Belsoft, and they also help with the ARM port, the AR64 port. And then Linaro pushes binaries via OpenJDK. Azul also provides binaries on ARM architecture. And when we're talking about Java, we cannot overlook the impact that Oracle has on all top of this. So the direction, like I mentioned, the long-term support releases, all those things are set by Oracle. Even many of the projects actually are led by Oracle. And I'm going to quickly talk about what that means to us. So in the past, before Java 9, we would have these major releases, and any kind of like language specifications that needed to be revised would go into those. And as you may have noticed with Java 9, it got delayed and delayed and delayed over years, right? And that was not an acceptable model for Oracle, so they changed it to something called long-term support and non-long-term support. What that means for us is that JDK 8 will be live and for a longer time for us. So many people who have not yet moved to Java 9 Plus still have time. But in this particular talk, I want to concentrate on why we should move to Java 9, what it has to offer. Java 9, as you guys know, is dead, right? So we're at Java 10 now. Java 11 is going to be released in September. So that's what it means when it says 18.9 and all. So those are long-term releases. For us, it means that the next one, Java 11, is going to be the long-term support. So, so when we're looking at these features, you will still find them in Java 11. And in fact, after that, as and when we have, like, for example, Project Loom, whenever that gets pushed, we'll have that going forward. So Java 11 will not have Project Loom, but whatever is the next LTS will have that whenever it gets released. So just to recap, JDK 8 is a long-term supported release. JDK 11 will be a long-term supported release. JDK 17, so if you see a pattern over here, will be a long-term supported release. And then the next would be JDK 23 and JDK 29, and so on and so forth. Okay? What is important to me is to understand, so as an architect, as a JVM performance architect, I need to understand the drivers of this ecosystem, what the stakeholders want and what is important to them. So we have, everything is based around the OpenJDK community. So we have the ecosystem that I covered earlier. We have the partners that I also covered earlier. And then we have the ARM customers, which are also our partners. And so these are the people that are driving the OpenJDK community. And we want to work with them. So what kind of helps these the stakeholders, right? Any kind of new CPU or microarchitectural feature helps them. For example, SVE really helps, like this scalable vector extensions is something that I will talk about when I'm covering the Project Panama vector API. I'll talk more about that. But these kind of features will help our stakeholders. And anything that, whenever you enable feature and you enable performance with it, that helps as well. So for example, for Java performance, when we give an example of distributed computing, back in the day before cloud, it was all distributed computing, right? Even cloud is a form of distributed computing. So what is that useful for? For e-commerce, where most of our customers also have e-commerce applications for services, in heterogeneous environments. So these services could be on different platforms. In containers, you can have distributed computing in containers. But what it boils down to is either they want, because of the containers, they want improvement in density, or they want improvements in responsiveness and/or throughput. They want to make sure that when we are talking about increased latency, we don't want to have a drop in throughput. So apparently, everything is important all the time. The more recent customers will talk about cloud computing. The more younger ones will talk about cloud computing. But again, they'll talk about it with respect to e-commerce for services in hybrid environments. So you can have your local cloud or cloud in the cloud, right? So, and again, containers. Again, the same three principles: startup, responsiveness, and throughput. So basically what I'm trying to say here is that it doesn't matter if it's cloud or distributed computing. What drives these stakeholders is improvements with respect to density, responsiveness, or throughput. So that's what I want to cover in the remaining time that I have. Let's start with startup. I want to talk about ahead-of-time compilation. This went into JDK 9. It was more kind of a restricted, a smaller an enhancement that was not fully supported, but it did go into JDK 9. And in JDK 10, so Andrew Haley of Red Hat actually ported that on ARM's architecture. So now on ARM, you can run this, run AOT compiled libraries as well. There's something called application class data sharing. String density, very important. Most of the improvements went in Java 9. Application class data sharing went in Java 10. So let's start with AOT. It's very new to HotSpot. If you've been a HotSpot dedicated user, then you know that it's something that everybody's been looking forward to for a long, long time now. But it's always been there, or at least for a long time now that I know of, in Excelsior Jet and also in IBM's J9. It helps to reduce startup time. Okay. How does it help? So some of the libraries, especially shared libraries, what you can do is you can have them ahead of time compiled and then just load it up, so you don't have to go through the slow or like tiered compilation. You could choose to do that, and I'll show you in a minute how to do that. But it really helps startup because of having it pre-compiled compiled ahead of time. It's built on something called the Graal compiler. Graal VM is new. Graal compiler is Java language written compiler. So if you know C1, C2, they're written in C++, but Graal is not. It's pure Java. And we use something called the JVMCI, which is Java Virtual Machine Compiler Interface. Just mentioning Graal here. So talking more about ahead-of-time compilation, there are two flavors to it, tiered and non-tiered. Tiered is the default. Non-tiered is the default, I'm sorry. And how can you get tiered with respect to AOT? So now when I say non-tiered is a default, that means once you compile it, that's what it is. But you could go and let your application, so you get good startup, but you can choose to have it go into tiered compilation. And how you could do that? You could enable tiered, and there's a threshold called AOT invocation threshold, which will, once you cross that threshold, those many invocations for that library, then you can go and gather profile data, and that will be recompiled in C1. So C1 will help gather the profile data. Eventually, you'll get to full profiling, and then you recompile it in C2. So you're getting this tiered advantage for your AOT code. So you have to use that option to enable tiered. And you use JAOTC to generate code. And you can look at that link over there if you want to get more information on how to do it. They have an example for doing the base module in Java. These are the command lines. So what is important to know is this AOT compile code resides in code cache. So keep that in mind when you're doing a big compilation, AOT compilation. It's going to come out of your code cache space. So when you're debugging, when you're trying to figure out what's happening, look at your code cache for AOT. For app CDS, so CDS, class data sharing, was something, and actually CDS was in Java 5, I think, and app CDS was something that was internal to Oracle, and they have recently open sourced that. It's really helpful when you want to use the same class with different processors. You have a multi-JVM application. But you're using similar classes, so you're sharing these classes. So it helps. So class data sharing, if it were a system class, then it already does that. I think for one of the GCs, you could invoke that. But now you can do that for for your user classes. So the classes that like custom class loaders, right? You can use that now. You can share it. So that's why application level class data sharing. I already mentioned that. So, like I said, it was closed source. Now it's open source into OpenJDK. It was done in Java 10. Really helps in reducing footprint and startup time because you're sharing your custom classes. So so you have to follow a bunch of steps. First, you have to get the class list, and then create the shared archive. Then you store the shared archive onto your. It actually goes into Metaspace, and then to use it, you will just invoke your shared archive. So, like I mentioned, the app CDS goes into Metaspace. So again, when you're debugging that, you have to look at your Metaspace. So Metaspace is what you would know PermGen to be. So since JDK 8, I think it became Metaspace. It's your native memory. So it's really important to understand where the code resides or where the classes reside. So it's in Metaspace. So it's going to be out of your native memory area. String density. So to reduce footprint, there's a lot of work that's been done in the optimizing strings field. The most important or biggest that you would see an impact, hopefully positive, but I've seen recent so internally we do a lot of experiments. So we're experimenting with compact strings on and off. But please try it with and without it and see if it helps your application. So what's the theory behind compact strings? So it's been observed that most strings contain Latin 1 characters. Okay? What that means is that we only need 1 byte for storage, right? But right now, we have 2 bytes for storage, because the backing array is a char array, right? So change the internal backing array from char to byte array. So instead of having 2 byte arrays, now we have a single byte array. And if you do need 2 bytes for UTF-16, then you go and use 2 byte array. So you only use 2 byte when you really need them. For the others, you don't need them, so you just use the single byte array. So what that means to you is that you can just basically feel the performance improvement without having to modify anything. So you don't have to rewrite your code or anything like that, because internally, the JVM engineers have already updated string builder and string buffer and everything for you. So you just get the benefits. Also, internally, the VM intrinsics have been updated. If you guys remember in JDK 8, I think, there was something called compressed strings, which would do something, but you have to compress and decompress it, the underline, the char array. Anyway, the point being, you don't need those kind of hacks now. So compact strings is much easier, much simpler, and more more in line with what gives you benefit out of the box. String density, there's more optimizations. Intern string, that itself is an optimization, right? When you're interning strings, and if string intern 1 is equal to string intern 2, then you just use the string object and the underlying, just use it once, the same one, right? So, but now you can store the intern strings in the class data shared archive. So this is even better improvement. This is only done for G1GC because you need to pin regions, and G1GC allows you to do that. 64-bit only with compressed oops and class pointers. The other thing is using invoke dynamic calls to JDK functions for string concat. So the theory is that any kind of modifications that we do to string concat internally shouldn't affect and shouldn't warrant Java C, so compiling a Java code to Java bytecode. We don't want that. So what we do is that we use invoke dynamic calls for your bytecode. So we can internally, whatever happens, we can change. So if you're passing a concat of a string and an int, you pass that as an argument internally to your string concat factory, and that's all handled in the bytecode level. So you don't have to Java C or Java code. And you can go and read more about it on that link over there. There are other density-related optimizations. For example, intern string that I mentioned. String deduplication in G1GC went in Java 8. What it does is the backing array is the same. So if there are two strings that are equal, then the backing array would be same. So you don't create another copy of the backing array. So you just point to the same backing array. So what about improving latencies? We have low latency GCs, Shenandoah by Red Hat, ZGC by Oracle. And then we have something called Project Valhalla. So let's talk about Shenandoah. Shenandoah does concurrent compaction, and it's only single generation. Prior to Shenandoah, all the OpenJDK garbage collectors had two generations, young and old. So Shenandoah is a single generation GC. It also does partial compaction. The main difference, so if you compare this with, and I'll compare it later to G1GC, but one of the main differences is Brooks-style pointers. So these are forwarding pointers that help with concurrent copying. These forwarding pointers are for every instance. Okay, so that's an overhead. And there's a concept of from space and to space. Any kind of update, like write, happens into the to space. So you always have two different spaces. It's region-based, just like G1. And Shenandoah needs read barriers to get data. So every time, even for reading, you will have barriers. So that's an overhead as well. There are different stages. The first one is the concurrent mark, which is the algorithm is similar to G1GC, which is snapshot at the beginning. It's a marking algorithm. There will be two small stop-the-world pause, one for doing the root, initial root, so which is called initial mark, which is piggybacked, I think, and then, so it's very quick. And then the final remark, which is at the end when your mutators are done updating the object graph, you want to have stop the world pause so that you can do a final remark. And then after the concurrent marking is completed, you want to do concurrent evacuation, which means you're concurrent moving, concurrent copying. And then you do the reference updating after you're done with the moving these objects. To help with this, with the concurrent updating, you can actually combine it with the next marking. So when you're doing the updating, you can, if you have a marking cycle, you can do it right then. So you can coalesce the two stages. Like I mentioned, major differences from G1, non-generational. Brooks pointers need additional word per object. That's an overhead. Read barriers themselves. G1 has no read barriers, only write, pre-write, and post-write. It does have write barriers as well. Now moving to ZGC. ZGC also is concurrent compaction. It is also single generation. It also does partial compaction. One thing interesting about ZGC is NUMA aware. ZGC is NUMA aware. G1GC is not yet NUMA aware. Parallel GC, if you know about the OpenJDK garbage collectors, the throughput GC, which is also called the parallel GC, that's the only one that's NUMA aware. So it's a NUMA aware allocator. ZGC uses colored pointers for concurrent copying. ZGC is region-based, and it does have read barriers to get the data, the right data. It does do concurrent marking. It has similar to Shenandoah. It has 2 stop-the-world pauses during mark start and at the end. What ZGC tries to do is budget for these pauses to be 1 millisecond or less. And if it is not able to do that, then it reworks the algorithm. It does concurrent relocation and compaction. So one relocation start pause is right there. And you also do concurrent update, remap, and relocation start. Again, the same concept. These kind of the concurrent reference updating can be coalesced with the next marking cycle. Major differences: not generational being one. Colored pointers, aka version pointers, which is very, very different. It's a new concept. The metadata is stored in 64-bit pointers. Okay, and so because of that, there's no support for compressed oops. So when you're using ZGC, you will always use it without compressed oops. There's virtual address masking, which is done in software for x86-64. So they do a multi-mapping, so they map it to different areas. But in hardware, on ARM architecture, we can actually use something called virtual address tagging, which is a hardware feature. And ARM engineer Stuart is actually working on that, and he has employed that already. He is an ARM assignee at Linaro. Heap regions have size groups, and you can have dynamic sizing. That's different than G1GC. You cannot, once you, at JVM startup, when you have the heap regions allocated, it's not dynamic. So that's different than in ZGC. And of course, we have read barriers, load barriers in ZGC. It's a big overhead as well. Project Valhalla, value types. You must have heard a lot about value types, actually. So to support immutable and reference-free objects, basically. There's generic specialization, which is talking about extending generics over specialized over primitives, for specialization over primitive types. And then there's various other things, and I think you're very much aware of that because Valhalla has been in the news for like almost a year or more. So I want to move on to throughput. So we covered footprint, right? And we covered latency, sensitive garbage collectors, which are the future of garbage collectors. And then now let's talk about throughput. So throughput. So as I mentioned earlier, G1GC is the default in Java 9 onwards, actually. So one of the lowest hanging fruit was to have parallel full GC support. Full GC in G1GC is a failsafe. It's a fallback. When your G1 cannot keep up with the partial compaction, and you're either because you have humongous objects, churn rate, or whatever, you end up filling up. Or fragmentation, you end up filling up and not being able to reclaim space. So you end up having to do a full compacting collection. In the past, before this change went in, it was done single-threaded. So imagine this large, huge heap that you have to compact now. It's done by a single thread. So it was very painful, like, you know, in the order of minutes sometimes. So now with parallel full GC, you can employ parallel threads. You can use the same parallel GC threads option that you have been using to have garbage collection threads being doing parallel work. Project Loom and Project Panama, these two are new, very important, very helpful towards the throughput aspect of the future of OpenJDK. And I'll talk about these, the SVE instruction set that ARM has. Parallel full GC first. I already mentioned there was the failsafe fully compacting collector. And I mentioned about the option to use. And remember that when I'm talking about parallel GC threads, that's the same option. What it also means that it will not only affect your young collection threads, but also the concurrent GC threads, which are 1/4 of this option, will also be affected. So when you change that, remember all the things in background. So your young collections, your mixed collections, and your concurrent threads will be impacted by that option. Project Loom. So if you worked with coroutines, you probably already know about Project Loom. It's something that we're bringing to Java, continuations, and having a runtime scheduler. It worked really well for Java. The concept is, and there's some work done by Pressler on this, where you can go and read that. So we use the fork join pool scheduler. We've already had this in Java. It's been tested, and we know what that is. So what that helps us with is having a lower footprint, right? Because we are now able to maintain our own thread. It's kind of like the concept of green threads. If you remember back when Java was very new, we had the concept of green threads in Java. We have the concept of green threads in Go routines as well in Golang. So it's similar to that. We have almost zero task switching overhead thanks to coroutines and the scheduler. And we're able to utilize our workflow. So if Java is in charge of scheduling the threads, then we're able to understand and utilize it better, the way we are scheduling the threads. So people that come, the younger crowd may know this as Fibres, also known as user threads or lightweight threads. Lightweight threads is not a new concept. OS level, we already are aware of lightweight threads. What this helps Java with is having no kernel interference. And the way we think of it is fiber blocking. That's the thought process behind it. So the users will write or convert your async code to blocking or synchronous code. Okay, and then because of that, you can make you can have scalable concurrency, which is much needed because Java thrives as a concurrent platform. Like it helps applications and code writers utilize concurrent APIs and concurrency of threads. So this will make it more scalable, and you will be able to get better synchronization, a more advantageous synchronization than what you would get when you would let the native, basically your operating system, handle that kind of stuff. Project Panama, it's the biggest buzzword, Panama, and there's because of two things. I'm sorry, something happened here. There you go. Project Panama. So the concept is to improve JVM interface, and how we interact with non-Java, right? So anything that's foreign to us. So think of it, native data accesses, and trying to get access to your heap, the Java heap, from inside or outside. So you calls from outside to the heap, or from heap to go to outside. New data layouts in heap. One of the most important things that you may have heard about is foreign function interface. So that can be intrinsified thanks to, this is already done for JRuby, and it's already studied for JRuby, and they're bringing it to Java now. So these are direct calls from JIT. The other part of Project Panama is to directly support hardware. So how do you do that? So Intel has already, let me talk about that in a minute. So Intel has something called the Vector API. So they have provided API support for vectorization. But the concept is to, if you're going to degrade, if you're going to use the least optimal instructions, then you want to do it gradually. It should not be obvious to you. For example, an older architecture that does not support vector APIs should still be able to not just give you, oh, I don't have those instructions and I'm not going to do anything. That should not be the case. You should be able to gracefully degrade. And then you want to be platform agnostic. You should not be able to tell, if it's an older Intel hardware or if it's Intel or ARM. So with this, with the Vector API for direct coding, ARM can take advantage of that. And SV is the future for vectorization, actually more so. It's more advantageous for auto-vectorization. So I'm going to quickly talk about that here. But it stands for Scalable Vector Extensions. So what is SV and ARM? Here's the link to the paper that you can read. But the whole concept is having scalable vector length. So you don't have vector for 512 or 256 or whatever, like dedicated lengths. These are scalable. And so this kind of helps, like I said, with parallelism, and hence auto-vectorization is an easy outlet for that. You can write scalable vector code. How that helps is that once you have already compiled it, you don't have to recompile it. So depending, again, of how your hardware can take advantage of that, it really flows with the Java concept of write once, run anywhere. It does gather, load, and scatter store again. Again, if you have read about auto-vectorization, you'll see how much of advantage that's going to be. I have 5 more minutes, so I'm going to skip through this. Non-linear access patterns are very important. So it's very easy when you have linear access patterns. You can always optimize it, and you can make it SIMD style, right? But when you have non-linear access patterns, that's very helpful with and vector API. This SVE instruction set can actually help you optimize and vectorize the non-linear access patterns as well. A few tools. External tools, we use Acing Profiler, Systat, and Perf. Perf is really important. Internally, we do instruction tracing. We have native Java agent as well that I mentioned earlier, and various simulators. This is Acing Profiler. It's right now I'm doing the allocation profiling. It's kind of stretched, but this was one run, and then so you can see the byte arrays, and this is using Java 10, I think. This is the Acing Profiler again. It's doing CPU profiling. So if you guys need to look into details of this, please go ahead and read about flame graphs by Brendan Gregg. And so basically, it's using those flame graphs to show you your profile of the application. This is spec JBB 2015. So you see all craziness, Oregon. But it's really helpful to see. It's kind of like a call stack, right? So you're able to see the call stack. This is the internal instruction tracing setup that we have. And this is a tool that I was talking about. It's up at Linaro Git repository. It's done by Steve Capper, who's an ARM employee, and you use perf record to record that, and then you use perf report. So you're using a native agent, so you get all these symbols. So this is how it'll look once you use once you do the perf recording with native Java agent. This is again spec.jbb, so you can see that you can expand on those plus signs, and you can see how hot it was. So it's a basic profiler for your CPU time as well as application. You can also do various perf counters, hardware counters, and get that information as well. I think that's pretty much it for me. And thank you very much. And it's a JSpring slide. Thanks.